I would like to thank the organizers for inviting me. The other interventions of this conference, which present advanced research, my presentation deals with some elementary aspects concerning the chemical bonds and structural aspects of molecules. I immediately state that then I refer to the distribution of the electronic cloud in space. I make some statistical simplifications useful to give an idea of the concepts I want to describe. This is presentation of a model which is called the ID model, from words ingegneria in Polish or ingegneria in Italian, words that mean engineering and design. I would like to begin this presentation with the comparison of the structure of the ring plane between the quantum mechanical model and the ID model of graphene. It can be intuitively noted that in the ID model, the carbon atoms have a dense reticulation of pi bonds at the level of the ring plane, which translates from a practical point of view into a significant increase in the force of cohesion between the atoms and therefore between the rings. This model of graphene was obtained by introducing follows innovations to the traditional ideas on chemical bonds. Firstly, interpretation of the electron pair not as a concentration of the electron cloud on one side of the nucleus, but as a symmetrical distribution of the electron cloud on both sides of the nucleus. Hypothesis that in polar bonds and the vast majority of multiple bonds, one electron is shared, not an electron pair, and therefore distinction of intermolecular bonds in bielectronic and monoelectronic. Thirdly, interpretation of the transformation of the geometry of molecules in relation to the number of bonds as a result of changes in the spatial relationships between atoms and not as a result of the hybridization of orbitals, and therefore prediction and calculation of the spatial parameters of molecules by applying trigonometric equation and other simple geometric rules. As the last one, hypothesis that the formation of multiple bonds in alkenes and alkenes occurs thanks to the transformation of bielectronic bonds into monoelectronic bonds where only one electron is shared. Momento. The result of sharing of a single electron in a bond, in example, the concentration of an electron cloud on one side of the nucleus, creates a bipolar orbital, the positive part of which, called here isotopia, attracts electrons. It is symbolically represented by an empty circle. The described method of interpretation of chemical structures implies the division of bonds in molecules into bielectronic, with the participation of two electrons equal covalent, and monoelectronic, with the participation of one electron equal non-covalent. When referring to monoelectronic bonds, the prefix mono will be used. The quantum theory of molecular bonds provides for a type of simple bond and a type of double bond. The introduction of monoelectronic intermolecular bonds varies and increases the possibilities of bonding compared to quantum mechanical models, as illustrated by the drawing below, which take into account only simple and double bonds. Note that in the ID model, the simple bond can be bielectronic or monoelectronic, and also that the double bond may not contain the pi bonds. We have two amphosynaptic bonds. The ID model does not foresee bielectronic pi bonds, since the reason for their formation is precisely the transformation of bielectronic bonds into monoelectronic ones. Now, here we have non-synaptic bonds. Monoshared and polyshared monoelectronic bonds that generate monohyperconjugation. In addition to the bonds described above, where only one electron is shared, polyshared monoelectronic bonds should also be considered, where the positive lobe of bipolar orbitals may attract more than one electron. Thanks to this type of bond, the carbons of graphene or graphite become hyperconjugated, allowing these compounds to develop a dense network of pi bonds, which makes their structure so cohesive that can exist in the form of extended films composed from a single layer of atoms. You have here mutual, non-mutual, and partially mutual bonds. The above mentioned principles of chemical bonds make it possible to interpret the structure of many controversial molecules, for example, carbonate or nitrate group, benzene, and above all, graphene, without having to resort to the theory of resonance and provide a new basis for the theory of hyperconjugation, in this case, monohyperconjugation. ID model, the formation of tetrahedral, planar, and linear molecules is not due to the presence of three types of orbital hybridization, because the mechanisms for creating different bonds is not to change the conformational geometry of individual atoms, but to change the spatial relations between atoms. Therefore, in alkenes and alkenes, the carbon atoms do not change the type of hybridization, but the cubic atoms, more or less symmetrical, come closer to each other, changing their spatial arrangement. This is symmetry statistic of orbitals in graphene, which allow each carbon atom to have 8 points of contact with nearby carbons. The following tables illustrates how the orbitals approach each other when creating multiple bonds. The approach of the orbitals involved in a bond occurs by rotating the atoms with respect to the bond, which is their axis of rotation. The semi-orbitals located at the same level in space will be marked with the same colors. Here we see rotation of ethane to form triplet ethylene. Here ethane, ethylene. Ethylene, this is rotation of ethylene, form alene or acetylene. In order to determine trigonometrically the bond lengths of molecules, one must relate the spatial relations of atoms to the spatial parameters of the cube, such as the edge length, L, and the length of two diagonals, as shown in the figure below. The change of the spatial relations between atoms determine changes in the spatial parameters of the molecules, so that these parameters can be dictated by applying simple trigonometric equation and other simple geometry rules. For example, alkanes, we can apply this equation for triple alkenes, and graphene, aldenes, alkenes. With the trigonometric equation, we found the following bond lengths, which vary slightly depending on the degree of unsaturation of the molecules. Measurements made with the ID model are very similar to bond length measurements obtained experimentally, such as those of triplet ethylene, graphene, aldenes, or acetylene. To achieve saturation, atoms for multiple bonds, converting the bi-electronic bonds into monoelectronic bonds, and changing the spatial relationships of the atoms so that the available electrons come closer to the lobes of positive bipolar orbitals, isolopias, which in fact contribute to the formation of multiple bonds. The mechanism for the formation of multiple bonds described here as an example of the conversion of ethane into ethylene and acetylene. Ethane lost two hydrogens. The carbon atoms of ethane convert bi-electronic bonds into monoelectronic bonds. Hence, the orbital becomes symmetrical apart from the carbon-carbon bi-electronic bond. And the atom can be described by deformed cube. The neighboring electrons and isotopias, positive and negative lobes of the resulting bipolar orbitals, attract each other. The attraction of neighboring electrons and isotopias cause the formation of mono-pi bonds and change in mutual spatial relations. In ethylene ID model, there is a sigma bond and 4 mono-pi bonds, so the bonds is triple. Now we see the bonds of acetylene. We see conversion of ethylene to acetylene, and we can see as in acetylene ID model, there are 2 monoelectronic synaptic bonds and 4 mono-pi bonds. So the bonds is quadruple. To finish this topic, I would like to make the comparison between the types of bonds in organic compounds between the quantum mechanical model and the ID model. In the quantum mechanical model, there are 3 types of bonds in organic compounds: single, double, triple. In the ID model, there are 8 types of bonds in organic compounds. The variety of bonds determines the variety of properties. In the bond diagram, the graphic scenes mean point, synaptic bond in the quantum mechanical model, and synaptic bond in the ID model. Line, lateral contact between the orbitals. After this brief introduction, we can describe the chemical bonds and structure of graphene. To understand the structure of graphene described in the ID model, it is necessary to investigate the changes in chemical bonds that already occur at the level of the transformation of cyclohexane into benzene, then transformation of benzene into substituted benzene, and therefore graphene. In the benzene, the carbon atoms, according to the quantum mechanical model, change the hybridization of the orbitals, forming a planar ring and maintaining the bi-electronic bonds between them. According to the ID model, instead, one electron of the bi-electronic bonds between two cyclohexane carbons moves to the other side of the orbital, to the other side of the nucleus, to form a monopi bonds. In this way, a transition state is formed in which the orbitals of the ring plane form the deformed planar hexagon. Each carbon of benzene engage 4 semi-orbitals in the bonds, 2 monoelectronics, synaptic bonds, and 2 monopi bonds. This representation of the effective statistical distribution of electrons engaged in monopi bonds. The electron cloud is shared equally between 2 carbons. It is assumed that the electrons of the planar ring plane repel each other, generating the return to the form of trigonal antiprism, non-counting the axial p orbitals, which represent the conformation in which the electron density, being more evenly distributed around the nucleus, it guarantees greater structural stability of the atoms. Therefore, the orbitals of benzene ID form 2 ring planes, the magenta plane downhill below the plane of the nuclei, and the indigo plane downhill above the plane of the nuclei. We see 3-dimensional structure scheme of benzene according to the model ID. This is effective statistical distribution of electrons. In the quantum mechanical approach, there is no difference in the chemical bonds between benzene and substituted benzene, except the polarization of the bonds in the case of the most electronegative substituent. In the ID model, the replacement of hydrogens in benzene causes a multiple transformation of the bonds. The substituted carbon of the ID model transforms the bi-electronic bond with hydrogen into a monoelectronic bond, and therefore the semi-orbital facing the ring in indigo are activated, which allow to form monopi bonds also inside the ring, contributing to the increase of its structural cohesion. The drawing shows in a qualitative and schematic way of purely illustrative value the distinction of the ortho, para, and meta positions, and the differentiation of the spin density of adjacent hydrogens. The structure of the graphene ring plane, in which we can consider a substituted benzene ring as elementary cell of the lattice, is characterized by a dense reticulation of monopi bonds inside of each ring. This dense cross-linking of monopi bonds within each graphene ring makes its structure exceptionally cohesive and strong, allowing the development of a stable spider web for a single layer of atoms. If to the monohyperconjugation of the ring plane we add the monohyperconjugation of the plane below and allow the ring plane, where each carbon can form up to 3 + 3 polyshirted monopi bonds, we can imagine the reasons of the exceptional structural properties of graphene. I would like to say, as a conclusion, as the ID model offers simple explanation in accordance with the experimental observation on the various questions regarding the structure of molecules and its properties. For example, in substituted benzene ID, the substituent causes an uneven charge distribution of differentiating the charge between adjacent atoms. Thanks to such a modified model of benzene, it is possible to explain various properties of these compounds and its derivatives. For example, differences in the spin charge density of adjacent ring hydrogens, distinguishing between activating and deactivating electrophilic substituents, degrees of aromaticity of condensate rings and monocycles, differentiation between ortho, para, and meta positions. The particularly important idea is that concerning the interpretation of mono-hyperconjugation of the bonds between the atoms of the substituted benzene ring plane. The table summarized very briefly some types of compounds that can be interpreted starting from the proposed model. Aromatic heterocycles, nitrogenous bases, aromatic monocycles and polycycles, graphite, graphene, and its derivatives. Thank you for your attention. I have finished.
Thank you very much, Dr. Justyna. That is time for questions. I would like to do one. Did you already validate your models with the experimental results?
Yes, I think as I told, as geometry and bond lengths and bond angles, it's we can interpret it very, very good with this ID model. Perhaps it's better as I ask to have my language supporter.
Okay, no problem.
It is easily explainable in theory by checking the geometrical angles and the lengths of the bonds, as Ms. Justyna said. So this was verified mostly theoretically, mathematically. Mm-hmm.
Yeah, thank you very much for your explanation. Let's wait a few more if there is someone questions. I think not. Thank you very much, Dr. Justyna, for your nice talk and conversation, and I hope to see you in the next conference.